Hi guys, so today we are jumping in to our very last unit of the year, which is gas laws, which is exciting. So we will be talking about today just kind of introing gas laws, as well as talking about our first one, which is the combined gas law. So gas laws basically kind of relate how gases are affected by changes in pressure, temperature, and volume. So we're going to start by talking about these different things. So we're going to talk about temperature and pressure, and then hopefully you guys know what volume is. So temperature, gas laws are related. Gas laws only work if your temperature is in Kelvin. So Kelvin is maybe a new temperature unit for you. So you have to be able to convert from Celsius to Celsius and vice versa. We don't need to worry about Fahrenheit. We don't use Fahrenheit in chemistry at all. So as long as you can get from Kelvin to Celsius or from Celsius to Kelvin, you are good. And it is super easy. So if I'm going from Celsius to Kelvin, all I'm going to do is I'm going to add 273 to that number. So your Kelvin temperature is your Celsius temperature plus 273. But then if I want to go from Kelvin to Celsius, I'm just going to subtract. So my Kelvin temperature minus 273 is my Celsius temperature. All right, so let's pop in and do a couple of these example problems. So for our first one, I have negative 167 degrees Celsius, and I need to convert that to Kelvin. So what I'm going to do is I want to go from Celsius to Kelvin. So there's my equation. So negative 167 plus 273. Go ahead and plug that into your calculator or do it in your head. But when you do, you should get that our temperature is 106 Kelvin. All right. Now then, I have 1,100 degrees Celsius, and I want to convert that to Kelvin. So I have, again, 1,100 degrees Celsius. I'm going to add 273 to it. And that gives me that my Kelvin temperature would be 1,373 Kelvin. Now then, for this next one, I want to convert 321 Kelvin to Celsius. So I'm using my other equation, which is Kelvin temperature minus 273. So in this case, I'm going to have 321 minus 273, which gives me a Celsius temperature of 48 degrees Celsius. All right, so I want you guys to go ahead and pause the video and work out this quick one really quickly. All right? Okay, hopefully you quickly worked that one. So it just says, how much does the temperature change in Celsius if it changes from 20 degrees Celsius to 255 Kelvin? So obviously we have to get them both to the same temperature here. So in this case, it's going to be Celsius since that's what it's asking for. So I just did 255 minus 273. Gives me that I had negative 18 degrees Celsius. So that means my temperature decreased by 38 degrees Celsius since I went from 20 to negative 18. So that's how we convert to Kelvin. Again, anytime you have any gas law, you need to convert to Kelvin. So just automatically, if your temperature is not in Kelvin, you must convert it. All right, so that's temperature. Next thing we're going to talk about is pressure. So pressure is the number of collisions and the force of the collisions on the walls of the container. All right, and our equation for pressure is actually force divided by area. Now, we have lots of different pressure units that you'll see throughout this unit, and they are kind of all equal to each other. So we have 1 atmosphere is equal to 760 millimeters of mercury is equal to 760 torr is equal to 1.01325 times 10 to the 5th pascals is equal to 101.325 kilopascals is equal to 14 psi. So these are all different units that you can see. So we have atmospheres, millimeters of mercury, torr, pascals, kilopascals, and PSI, which is pounds per square inch. These are all equivalent. So if like you were given two different pressure units, we could actually use these as conversions to convert between pressure units to make sure they end up the same. So like if I had atmospheres for one of my pressures and PSI for another, I could use this to convert between them. So yeah, those are our pressure units. So just be looking out. You just kind of need to know them and know what your pressure units are there. All right. One more thing we're going to talk about before we jump into the gas law relationships is how gases actually behave. So we talked about this a little bit in the KMT solutions unit. But since this unit is all about gases, we're going to have a quick refresh. Basically, there's 5 postulates of the way that gases behave. The first one is that gas particles are small, and they're so small that we say that they have insignificant volume, and they are extremely far apart. So what that means is like if I have a container, my gas particles are just like so small compared to the volume of my container that we can consider them negligible. And then the space, compared to their size, the space between the gas particles is huge. All right. Then there is no attraction or repulsion between particles. So gas particles aren't attracted or repulsed by each other. They move in a constant straight line motion. And there's only elastic collision. So elastic collisions means that our energy is conserved in a collision. And the kinetic energy is dependent upon temperature. So as temperature increases, your kinetic energy of your gases is going to increase. And all gases will have equal kinetic energy at the same temperature. So that's just kind of how gases behave. All right. So now what we're going to jump into is we're going to jump into relationships. And we're going to start with these baby relationships of Boyle's, Charles, and Gay-Lussac's law. All right. So Boyle's law tells me when temperature remains constant, volume and pressure vary inversely. So what that means is that as my volume increases, that means that my pressure is going to decrease, or vice versa. So they vary inversely, so they're opposite. So as my pressure increases, my volume is going to decrease. And I remember this gas law personally with the phrase, you boil peas and veggies. So Boyle's law relates pressure and volume. All right. If I was to graph Boyle's law, I would have pressure and volume on my graph, and it would be an inverse graph, so it would look like that. So as my pressure increases, my volume is going to decrease, and as my pressure decreases, my volume is going to increase. These all do have little baby equations that go with them. I'm going to show you all the equations, but really we'll use the overall equation that combines all of them together. So the law for Boyle is P1 V1 is equal to P2 V2. So pressure 1 times volume 1 is equal to pressure 2 times volume 2. So again, important things to know is that Boyle's law relates pressure and volume, and they are inversely related. All right. Next law, we have Charles' law. And Charles' law is constant pressure, and it tells us that temperature and volume vary directly. So what that means is that if my temperature goes up, then my volume is going to go up. If my temperature goes down, then my volume is going to go down, and it'll be proportional. All right, I remember this one by Charlie on TV. So I don't know if you guys, well, hopefully you know, Charlie Brown. Charlie Brown is a TV show. So Charlie on TV, Charles' law relates temperature and volume. Again, if I was to graph Charles' law, I would have volume and temperature. It's a direct relationship, so it just looks like this. So as my volume goes up, my temperature also goes up, and it is proportional, so it looks like that. And our equation is, for Charles' law, is V1 over T1 is equal to V2 over T2. All right, so again, the important things to know here is that Charles' law relates temperature and volume, and they are directly related. So as temperature goes up, your volume goes up. And our last baby gas law is going to be Gay-Lussac's law. So this one says when volume remains constant, pressure and temperature vary directly. So again, what that means is that when my pressure goes up, if my pressure goes up, then my temperature is also going to go up. My pressure goes down, my temperature is also going to go down. And I remember this one with the phrase Gay-Lussac drives a PT Cruiser. And I've learned that a lot of y'all, that they don't make PT Cruisers anymore. So a lot of people don't actually know what a PT Cruiser is. So you could also think of Gay-Lussac as like a physical therapist. You can come up with your own. Or Google what a PT Cruiser is. It's a car. So it's not anything super exciting. But Gay-Lussac drives a PT Cruiser. So this one relates pressure and temperature, and they are directly related. So we have that same graph there. And the overall equation for this one is P1 over T1 equals P2 over T2. So the important thing to remember here is that for Gay-Lussac's, it's relating pressure and temperature, and they vary directly. So that's hopefully those little phrases are helpful. There is kind of one more phrase that you can use to help you remember, but this one is more focuses on which stays constant. All right. So the phrase that helps you remember which one stays constant is to play baseball, you need your bat, you need your cap, and you need your glove. So for Boyle's law, temperature is constant. Charles' law, pressure is constant. And Gay-Lussac's law, volume is constant. So bat, cap, glove. Just whatever makes sense for you. But just to remember those different relationships. Now, I've given you equations for all of these, but we really haven't used them for anything. And that's because we are going to use the combined gas law, which basically takes Boyle, Charles, and Gay-Lussac's and just pushes them all together and combines them all together. And there we get the combined gas law. So we would use the combined gas law when all three variables are changing. So when pressure, volume, and temperature are all changing. Remember, temperature must be in Kelvin. Our pressures must be in the same units. It doesn't matter which one, as long as they're the same. And then volume must be in the same units. And here is our overall equation for the combined gas law. All right, so it's P1 over V1, over P1 times V1 over T1 equals P2 times V2 over T2. This is on the back of the periodic table, the formula chart back there, so you don't have to remember it. And again, remember your temperature must be in Kelvin. My phrase for this one is peas and veggies on the table. So pressure and volume over temperature. I think that's a fun little phrase. So peas and veggies on the table. All right, one more thing before we jump into doing some actual math and some actual practice with this. Sometimes your problems may ask about STP. STP stands for standard temperature and pressure. So standard temperature is going to be 0 degrees Celsius or 273 Kelvin, and standard pressure means 1 atmosphere, or any of those equivalent ones. So we learned up here all of those equivalent ones. So standard pressure could be 1 atmosphere, 760 millimeters of mercury, 760 torr, 1.01325 times 10 to the 5th pascals, 1.01 101.325 or 14.7, just depending on it. So any of those could also be standard pressure since they are all equivalent. Okay, so we are going to jump in now to solving these problems. What's going to be really important in solving these combined gas law problems is going to be knowing your variables and making sure you label them. All right, so let's start up here. So this is a 3.5 centimeter cube sample of nitrogen whose pressure is 79.1 kilopascals, expands to 6.10 centimeters cubed, while its pressure also changes to 91 kilopascals. At the expanded volume, the temperature of the gas is found to be 28 degrees Celsius. What was the original temperature Celsius? So first thing we're going to do is we're going to go through and find all of our variables and label them. So we have a 3.5 centimeter cube sample. All right, so 3.5 centimeter cube sample. That centimeters cubed is a measure of volume. So that is going to be our V1. And if we keep reading, it says whose pressure is 79.1 kilopascals. So that goes with that volume sample. And so that is going to be our P1. It's then expanded to 6.1 centimeters cubed. All right, so we have 6.1 centimeters cubed. That is going to be our V2 because, again, it says it's expanded and we have another volume. So that's going to be there. That's going to be our V2. While its pressure also changes to 91 kilopascals. All right, so that's going to be our P2 because it's a pressure. At the expanded volume, so at our bigger volume, the temperature of the gas is found to be 28 degrees Celsius. So that is going to be our T2 because we're at the bigger volume. Now remember that our temperature must be in Kelvin. So we're going to take that 28 and add 273 to it. So plus 273 gives us that our T2 temperature is going to be 301 Kelvin. And then what are we looking for? We want to know the original temperature in Celsius. So we're looking for T1, sorry, not T2, the original temperature, T1. All right. Then from there, it's just plugging in our values. So we have P1, V1 over T1 is equal to P2, V2 over T2. So we're going to go ahead and plug it on in. All of our units are in the same, so we don't need to do any conversions since they're all the same. So I have 79.1 kilopascals times V1, which is 3.5 centimeters cubed, all over T1, which is our unknown, is equal to P2, which is 91 kilopascals, times V2, 6.10 centimeters cubed, all over T2, or I know T2, I don't know, guys. I'm struggling with plugging things in, apparently, which is 301 Kelvin. All right, now to solve this, we're going to do some great cross multiplication. So I'm going to multiply all of these three numbers together, and all of this together in order to get my cross multiplication going there. All right, so go ahead, plug those on in, do your cross multiplication. And when I plugged it on in and got my cross multiplication, I got 83,331.85 is equal to 555.1 times our T1. I want to get T1 by itself, so I'm going to divide both sides by that 555. So I get T1 is equal to, when I plugged it in, I got 150.1204, so on and so forth. We do need to check our sig figs here. So we're multiplying and dividing. So we're going to go with our fewest number of sig figs, which I see that 3.5 is our fewest number because it only has 2 sig figs. So my answer should only have 2 sig figs. So I get 150 Kelvin. However, I'm not quite done yet because it wanted the original temperature in Celsius. So to get back to Celsius, we are going to subtract 273 to get that our new Celsius temperature is negative 123 degrees Celsius. And that's it. That's how we do the combined gas law. All right. Let's do another one together. All right. And then I'm going to have you guys do one on your own. So it says, what would be the volume of an 8.90 liter sample of gas at 110 degrees Celsius and 113 kilopascals if conditions were changed to STP? All right, so what we are looking for here is it says what would be the volume. So that's going to be our, we're obviously undergoing a change here, so that's going to be our V2 of an 8.9 liter sample. So liters is again volume, so that's going to be our V1 of gas at 100 degrees Celsius. So 100 degrees Celsius will be our T1. And again, we need to go ahead and convert that to Kelvin. So we're going to add 273 to it, which gives us 373 Kelvin and 113 kilopascals. So that's going to be our P1. If the conditions were changed to STP. So now you guys might be thinking, okay, well, we don't have all of our variables because we don't have P2 and we don't have T2. But we do, because if you remember, STP stands for standard temperature and pressure. So standard temperature is 0 degrees Celsius or 273 Kelvin, which will be our T2. And standard pressure is, standard pressure is going to be our, is 1 atmosphere, or in this case, we're in kilopascals. So standard pressure is going to be 101.325 kilopascals. All right, and then we'll just plug it on into our equation. So P1 V1 over T1 is equal to P2 V2 over T2. All right, so I have 113 kilopascals times 8.90 liters divided by T1, which is 373 Kelvin, is equal to P2, which is 101.325 kilopascals times our second volume, all over T2, which is going to be 273. So once again, we're going to do our cross multiplication here. So we're going to multiply all of those and multiply these together to get our the next part of our equation. So do your cross multiplication. So 113 times 8.9 times 273. And when I did that, I got 274,556.1. And then when I cross multiplied the other ones, so 373 times 101.325, I got 37,794.225 times V2. So we're going to divide both sides to get V2 by itself. So divide both sides by that 37,000. And we should have 3 sig figs in our answer because we have, that's our fewest number of sig figs in our problem. So we get 7.26 liters as our volume. Boom. All right, guys, I want you guys to go ahead and try to solve this next one. I want you to notice that it says its volume will not change. So when it says that, basically we can cancel volume out of our problem. We don't have to solve for volume. So I want you guys to go ahead and try to solve this one, see how you do, pause the video, work it out, and then come back to go over it. All right, guys, so like I said, it says volume will not change. So I can actually cancel volume out in my overall equation since it's going to stay the same on both sides. So it had a pressure of 1.41 atmospheres. When the temperature was 80 degrees Celsius, we need to convert that to Kelvin. So I added 273 and I got 353. What would be its pressure? So we're looking for P2 if the temperature changed to 35 degrees Celsius. Again, got to convert that to Kelvin, so it's 308. So then we just go ahead and plug it on into our equation. And when I did, I got that my pressure should be 1.27 atmospheres. Again, remember, if something isn't changing, if it says like temperature's not changing, pressure's not changing, you can just cancel it out of your equation and you don't have to plug it in. And then if you notice, what baby gas law are we using? Well, we're using Gay-Lussac's law. P1 over T1 equals P2 over T2. All right, there are 2 more problems on here, so I want you guys to work those out on your own as practice and then check the answer key to see if you got them right. All right, have a great day, guys. Bye.